split to half S2, split to half S3, all the way up to S3. Okay? Now,
in the theorem you wrote x1 up to xd, so you have to do
yeah, only D. Only D. Here we have another one. We cannot. S1 up to SD, they split it to half. SD plus 1,
You don't know.
I don't know, but SD plus 1, I still know one thing. For SD plus 1, I know in one of the sides there will be more than half, or more equal to. So let's say that here, let's say that SD plus 1 intersect H plus is greater or equal to 1/2 of SD plus 1. So in one of the sides there will be at least 1/2. And now, what we will do, we'll do the following sneaky trick. We will take, for the S1 up to Sj, we will take the intersection with H minus. We'll take this part. Okay. For Sj plus 1 up to Sd plus 1, we will take the intersection with H plus. And this will be our new sets. So what did we lose? We lose for every of the sets, we lose a factor of 2. And for the last set, we lose a factor of less or equal to 2. So this is the price we pay. What is the gain we get? Now we know that S1 up to Sj is separated from Sj plus 1 up to Sd plus 1. How do we know this? Because it's separated by this hyperplane H. Okay? So this is so we make it separated. Okay. And now we repeat this process for every subset, for every partition of the D plus 1 sets into 2 parts. Altogether there are, we don't care about partition, the complement, we have 2 to the D such partition. For every such partition, we make this argument. If things are as worse as possible in each such step, we reduce the density by half. And this will replace the original SIs by new SIs, which are separated, and the size is 1 over 2 to the power 2 to the D. Okay. And now we do the same trick. Now we want also to add the vertex, the single point O. So we want also that if we take the D plus 1 set, S1 to SD plus 1, and O, this will also be separated, which means that every time we take O and we consider all these sets except 1, this is well separated. And then we can do the same argument, except in the Ham-Sandwich theorem, the hyperplane will always contain O. So this point O will never be removed. But again, with additional 2 to the D steps, we separate O from S1 up to SD, and we have to do it for every subset. So by splitting all the sets 2 to the D times D plus 2 times, making this operation which cut the size of all these sets by half this many times, we achieve that the points are separated. Okay, so so now what does it give us that the points are separated? Okay, so now let me write this too. So now we have new set of points. So we have T1 up to TD plus 1. Ti is a subset of Si. The size of Ti is greater or equal to 1 over 2 to the D times D plus 2 times the size of Si. And which is epsilon times the size of Si. So and the Ti's are well separated. The conv T1 up to conv TD plus 1 and the set which contain only O are separated. Okay. And what else do we know? We know that E of T1 up to Td plus 1 is greater than 0. So we know that there is a multicolored simplex in our hypergraph where one vertex is in T1, one vertex is in T2, one vertex is in Td plus 1, which is in a hypergraph. What does it mean? It means that if we look at the, so here is T1, here is T2, here is T3, in our case here is O. We know that there is a triangle where one vertex is in T1, one vertex is in T2, one vertex is in T3. In D dimension we have a simplex with D plus 1 vertices. So that this triangle contains O in the convex angle. But now, what do we know? What does it mean that these points are separated? It means that the order type, if we choose one point from T1, one point from T2, one point from Td plus 1, and the point O, we know that the order type is always the same. And this means that if O belongs to this triangle, it will also belong to every other triangle. So this means that this is the conclusion. So from theorem 4, we know that every choice of one point in T1, one point in T2, one point in D plus 1, and the point O, every such choice has the same order type. And if for one such choice O belongs to the convex hull of the simplex, then this is true for all the choices. So this is the end of the proof. Okay, so this concludes the proof of Park's theorem. And after the break, we will complete some of the pieces we need for the individual ingredients, and we'll mention some problems regarding further generalization. But it's sort of a nice theorem.